Welcome to the Subverse. I'm your host, Susan Mathews. This is a podcast where we journey from the cosmic to the quantum, from the complexity of development to the art of resistance, from colonial histories that haunt us to reimagining futures. My guest is Ferris Jabr, author of a wonderful book, Becoming Earth: How Our Planet Came to Life, published in 2024. Ferris is also a prolific contributing editor for the New York Times Magazine and Scientific American. In this book, he writes that we and other living creatures are more than inhabitants of Earth. We are Earth, an outgrowth of its physical structure and an engine of its global cycles. Earth and its creatures are so closely intertwined that we can think of them as one. The notion that living creatures of all kinds might modify their environments in much more dramatic ways, that microbes, fungi, plants, and animals can change the topography and climate of a continent or even the entire planet, was rarely given serious consideration. But in this book, Ferris Jabr explains how all this happens. While we know now that humans are the most extreme example of life transforming Earth in recent history, we are far from the only creatures with such power. As he writes, the history of life on Earth is the history of life remaking Earth. It was such a thought-provoking conversation filled with amazing facts, and Ferris speaks as he writes, very eloquently. From a Jules Verne-like journey to the center of the Earth, we end in a Led Zeppelin-like stairway to heaven. Hope you enjoy the episode. Ferris, I would like to warmly welcome you to the Subverse. Thank you so much for joining us today.
Thank you. No, it's my pleasure to be here.
Great. I would like to start with what I think is the central question in your wonderful book, Becoming Earth, which is, in what ways and to what extent has life changed the planet throughout its history? In the book, you write that all manner of life forms, from microbes to mammoths, have transformed the continents, ocean, and atmosphere, turning a lump of orbiting rock into the world as we've known it. Can you tell us more about this theme and how this has been influenced by and/or differ from other theories along the way, such as the Gaia hypothesis?
For a long time, Western science in particular has segregated geology from biology and has regarded planet Earth, essentially as a giant rock that happens to have some life on it because it was in the right place in the cosmos. And it has minimized the role of life in shaping the planet as a whole. And now there's a big shift happening in the world of science where there's this growing recognition that life and the planet change each other continually through time. And that, we cannot so neatly segregate the biological from the geological. And in fact, we can think of the planet as a whole as this vast interconnected system, perhaps even a living, self-regulating system. And these kinds of ideas have become the pillars of a fairly new mainstream field called Earth system science, which explicitly takes a holistic view of the planet and studies the connections between the animate and the inanimate. And this kind of thinking has ancient antecedents. Throughout history, throughout world cultures and religions and mythologies, we see this idea of the world being alive over and over again. For much of, the recent history of Western science, such thinking was really criticized, even ridiculed. And the most famous articulation within Western science was the Gaia hypothesis. This was conceived by British scientist James Lovelock in the 1960s, and then later developed with American biologist Lynn Margulis. And what they proposed was that wherever life emerges, it will inevitably transform its home planet, and that together life and the greater planetary environment form a single self-regulating living system. They were really interested in the ways in which life kind of loops back to alter the planet as a whole, and the ways in which it can improve the habitability of the planet over time. When Lovelock first published his book on Gaia and started writing about it and talking about it, he received a lot of intense pushback from the scientific community, especially from evolutionary biologists. And in recent decades, however, that kind of opposition has diminished to some extent because we understand these systems a lot better than we did 50 years ago. And, there are many scientists who now think of planets as either alive or dead and are interested in that distinction. So my book is really exploring this new way of thinking about the planet, this new understanding, which is simultaneously ancient and modern because it has a very rich history behind it, but it is being re-examined, reworked right now for the 21st century, for the Anthropocene.
Thank you so much, Ferris. I'd like to really get stuck into your book, and I'd like to use the way you've actually divided the book, which is that you have three main sections. You have rock, water, and air, which mirror the planet's main elemental components and spheres, the lithosphere, the hydrosphere, and the atmosphere. And I'm going to follow that scheme in my next set of questions. You start with the Earth's crust and the unexplored recesses of Earth's rocky interior. I really love this part as it reminded me so much of Jules Verne's books, which is something you also refer to in these chapters. So if you could start with this journey which you take in this metal elevator called the cage, and if you could speak about the role of underground microbes or intraterrestrials, as you term them, in shaping Earth.
Sure. Yeah. So just a few decades ago, we did not think that there was any life of any kind in the crust, more than a few meters below the surface. And likewise, we didn't think there was any life in the clouds high above us. And we now know that actually there is microbial life in both of those extreme places. The microbes that live in the deep crust inhabit these pores and fissures in the rock that are filled with water. And they're very strange. They're very different from surface microbes. They don't get energy from sunlight or oxygen. Much of the time, they've evolved to breathe rock and metal or eat rock and metal instead. And they seem to be able to live for a very long time, and they're extremely resilient. And so if scientists want to study these microbes, they have to find a way to get deep into the earth. And often they will use mines to do this. So in South Dakota, there is a former gold mine, the former Homestake gold mine, that's been converted into a scientific laboratory. Most of the scientists that go there are actually physicists that are conducting specialized experiments that have to be shielded from cosmic rays. So they travel about a mile below the surface of the planet, and they use that mile of rock around them as a shield from the cosmic rays. I went with a team of geomicrobiologists. So these are biologists that study microbes, and then specifically they're studying microbes that are intimately involved with the planet's geological processes. And so you go to the mine, and then you get in this bare metal elevator called the cage, and it takes you about 10 minutes to descend a mile beneath the surface of the planet. And then you travel through these narrow tunnels and chutes of rock and these little rail cars, on these old mine tracks. It kind of feels like a theme park ride sometimes, and you're just kind of restricted to these very narrow, dark tunnels. The only light is coming from your headlamps on your helmet and such. So it's a very unique experience. For anybody with claustrophobia who doesn't like tight spaces, it's not a great place to visit. And you rationally, that there's sort of 3 Empire States buildings worth of rock above you, but you can't really see it because you're just traveling through these tiny tunnels. And there are places down there that are so hot and muggy that you could only remain in them for a few minutes at a time before you have to back away to a better ventilated area. So there are some places where, you can really feel the Earth's inner heat. Its inner fire is just soaking through the rock, and it's just so stultifying down there. But then there's other spaces that are much larger, and there's wind and air moving through them constantly, so they're actually quite cool. So yeah, it's a place of intense extremes. And we now understand that these microbes don't just live down there. They actually are involved in the planet's geology in really interesting ways. So, microbes, they can contribute to carving vast underground caverns. They can concentrate precious metals that eventually become ores or reservoirs of gold or silver. And there's a really interesting theory that microbes may have played a role in the formation of the continents. So the continents are made of granite. And we've never found granite in any great abundance anywhere else in the solar system, only on our planet. And that might be because life was important to its initial formation. So granite is less dense than basalt. So basalt is what comprises the oceanic crust. So the terrestrial crust, the continental crust, floats on top of that basalt because it's less dense. And the theory is that granite was initially formed through a subduction and melting and recycling of the denser basaltic oceanic crust. And a long time ago, microbes, by inhabiting that ancient crust and dissolving it with their metabolic activities, they were bringing in water and hydrating that crust. They were bringing in these wet clay mineral byproducts. So they were hydrating the crust, making it wetter, lubricating it essentially, and that sped up this process of subduction and recycling and melting, and it sped up the production of granite. So the thinking is that if it weren't for the activity of these ancient microbes, we wouldn't have made as much granite on the planet as we would have with their presence and activity. And if it weren't for life, we may have ended up with much tinier continents, much smaller land masses, and Earth would be even more of an ocean world than it is today. So it's possible that microbes are really important for sort of laying the groundwork for all other terrestrial life. That was my journey. That was my personal journey, a small way towards the center of the planet and, exploring these fascinating microbial residents along the way.
I must say, it's so fascinating to hear about the role that microbes have really played in mineralization. And like you said, I love this term that you use in the book, which is microbial terraforming. And it's a wonderful term. I mean, imagine something this tiny, which is shaping continents. It's a fantastic way to kind of describe it. Here in the book, you talk about this microbial life underground, but then you also talk about the role of titanic creatures. Here you move to is the mammoth steppes in the Arctic. And if you could tell us a little about the role of, elephants in the savannas.
Right. So there's this interesting idea in ecology, fairly new idea, zoogeochemistry, which is that we have to really put animals back at the center of planets' nutrient cycles and not just look at them through a geological lens. If it weren't for animals, all of the vital nutrients and elements we depend on would tend to get stuck in place and wouldn't move through the planet's layers as fluidly as they do right now. For example, in the ocean, you have whales, simply through their sheer size and movements, they're circulating oxygen and carbon and nutrients through the ocean's layers. Then you have migrating animals like seabirds and fish will bring some of those nutrients back to land. And then bears and otters will eat those fish from the rivers and leave their carcasses on the riverbanks. So then the carcasses are fertilizing the forest soil. And then the plants and trees in the forest are breaking down the rocks that then flush more minerals back to the ocean via rivers. So there's this really fascinating zoological, ecological loop. To explore this idea, I traveled to an experimental nature park in Siberia called Pleistocene Park. And a team of Russian scientists are bringing back large grazing animals to this landscape to try and revive ancient grasslands, some version of the ancient grasslands that existed there tens of thousands of years ago during the Pleistocene. So it used to be that these really massive, thriving grasslands, ringed the entire northerly latitudes of the planet. And they were full of mammoths and mastodons and ancient bison and ancient elk and all these fascinating large grazing species and also carnivores that ate them. And these Russian scientists have this theory that the grasses and the grazers formed a very powerful symbiosis and sort of maintained each other through ecological, great spans of geologic time. For example, just through their size and heft, large grazers will trample these shrubs and trees that would otherwise compete with grasses, and they'll fertilize the grasses with their dung. And then the grasses are providing them with this rapidly regenerating vegetation that they can continually graze. The large grazers that are also stripping away layers of snow that would otherwise insulate the grasses, and they're allowing the frigid temperatures to penetrate deeper and keep the permafrost frozen. Whereas right now we're seeing a lot of thawing of permafrost. So their thinking is that if they can recreate the grasslands, they can help keep that permafrost frozen. It's a really huge challenge to do what they're trying to do. They've been able to bring some bison and other large grazers to this area, and they've been able to convert some of the sort of swampy tundra into grassland, but it's just such a challenge to do it on the scale that they really want to do. And it's just such a vast wilderness out there. But large animals, large grazers are doing this kind of activity all around the world. They're doing the same thing in Africa. Elephants are likewise extremely important ecosystem engineers in the savannas of Africa. They're changing the landscape by pushing down trees, by grazing on vegetation, by spreading seeds. And even their footprints have a massive impact on the ecosystem because a single elephant footprint can fill up about 50 gallons of water. And that becomes a really vital pond for many other species and creatures, for all kinds of insects and larvae and amphibians and reptiles. And so just by walking through their environments and leaving behind a trace or an impression of themselves, elephants are creating entirely new worlds, that are then inhabited by other creatures that would otherwise have no access to ponds of any kind. And so to think that kind of, ecosystem engineering has been going on for millions of years through mammoths and mastodons and bison and elephants, but it's only recently that we've actually paid attention and discovered these effects is really astonishing. So animals as, dynamic entities are hugely powerful engines of ecological cycles on our planet. And scientists are paying a lot more attention to that now.
Here, of course, we've spoken about the microbes and we've spoken about titanic animals, but there are also creatures like earthworms and beavers, all who have played a role.
Yeah, absolutely. It involves, the whole spectrum of life.
Ferris, I'd love to move now to the next sphere, which is water. And here we could talk about plankton, which is found in every liquid environment. So cyanobacteria and other microbial ocean-dwelling phytoplankton are Earth's original photosynthesizers. Without plankton, the modern ocean ecosystem would collapse and affect carbon sequestration. So could you tell us more about this almost invisible life thread in some forms that has sculpted and nourished our watery realms?
Yeah, the plankton chapter really sits at the heart of the book, and plankton really fascinated me. I mean, first of all, the sheer diversity and beauty of plankton is truly mesmerizing, especially these single-celled plankton that a lot of us don't know about, like diatoms and radiolarians, foraminifera, and all these other amazing planktonic creatures. Many of them encase themselves in these exquisitely sculptural shells and skeletons, which they make from chalk or from glass, from limestone or silica. And you can see their beauty if you look at them through very powerful microscopes. And some people, like the naturalist and illustrator Ernst Haeckel, was totally obsessed with them and drew very meticulous diagrams and illustrations of them that are still used today and still marveled at. And the Victorians were so obsessed with them that they would take a single hair from a boar or a horse, and they would use it to arrange jewel-like plankton on a microscope slide into miniature mosaics of something like a vase of flowers. And then they would invite people to their salons and their cabinets of curiosity to marvel at these miniature jewel-like creatures through microscopes. And so plankton are really suffused throughout basically every part of the Earth's system. They're in the water, they're in the crust, they're in the atmosphere, they're everywhere. And they're so ancient and tiny and fundamental that they really influence everything. In the ocean, they are the foundation of the marine food web. They are doing half of the photosynthesis on our planet. They are producing huge amounts of oxygen, and they are taking vast quantities of carbon to the sea floor as they die and sink to the sea floor and accumulate in these sediments. And these sediments, they petrify over time. They're compressed under such intense pressure and heat that they turn into stone. And then that stone actually becomes part of the Earth's bones and structure over time. So, for example, if you chip off a piece of chalk from the White Cliffs of Dover and you look at it under a microscope, you will see the remains of ancient plankton that lived in the ocean more than 60 million years ago and then accumulated in layers of seafloor sediment, turned into chalk, into limestone, and then were exposed by changing sea level. That's what the White Cliffs of Dover are. They're a massive accumulation of the remains of ancient plankton. And so it's basically a massive fossil bed, not just ordinary rock. And in fact, the vast majority of limestone formations across the planet are made of the compacted remains of ancient plankton, which means that all of the monuments we've built with limestone, like the Colosseum and Notre Dame and the Washington Monument, they're also made of plankton. Some of the stone materials that our human ancestors relied on to make stone tools millions of years ago, like flint and chert, they're also made of the remains of plankton. So they're really all over the place. And there are these incredible dust storms that blow over from Africa to South America and fertilize the Amazon rainforest. And that dust is itself made of ancient plankton because it's coming from an ancient lake bed in Africa. And so you have these ancient plankton blowing over across an ocean and then fertilizing the largest forest and largest ecosystem on the planet today. Plankton are also large part of why the ocean smells the way it does. They often make up sands on beaches, and they really are just everywhere you look. They're in the scents and the colors of the planet. And yeah, they're just truly amazing creatures. So I was just really fascinated by their diversity and just how influential they are on planetary ecology.
We'll be back after a break. Thank you so much, Ferris. And here I have a question, which is that obviously, things are changing in the ocean rapidly and not in a good way at all. So how do these changes now affect plankton? And in turn, how will that affect everything else?
Yeah, I mean, one of the biggest changes to the ocean right now is acidification. So the ocean is becoming not only much warmer, but much more acidic than it's ever been in the past, or than it's been for a very long time. And the acidification is a huge problem for plankton because it literally, at a certain level, begins to dissolve them because they construct their shells from calcium carbonate, and that requires a certain pH to exist in a stable form. So if the pH gets too low, if the ocean water becomes too acidic, they literally start to dissolve and fall apart. And that would have massive consequences for the marine food web and also the carbon cycle within the ocean. Another really fascinating and also kind of horrifying change that I really became engrossed in is plastic pollution. And there's an interesting link here to plankton because plastic is made of petroleum. And petroleum is made of the remains of plankton that have been cooked and compressed deep within the earth. And then we end up polluting the ocean with plastic, and it turns into all these microparticles. And these microparticles of plastic end up mimicking real plankton in very strange ways. So they start to absorb the smells of the ocean, and then larger animals will eat the plastic thinking that they're plankton or that they're their prey. And then the plastic starts to sink to the sea floor the same way that plankton does in what's known as marine snow and accumulate in these seafloor sediments. And we don't know how that's going to affect the carbon cycle because it's such a new phenomenon. So I've started to think of plastic as a kind of necromancy, that we're reviving these ancient plankton and then polluting the ocean with them. The plastic particles are becoming ecological imposters that are mimicking real plankton. And we honestly don't know what the consequences will be because it's just so new. But that's something that scientists are paying attention to now.
And now I'd like to move on to the atmosphere, which is the third sphere that you talk about in your book. And in this particular chapter, you start by talking about something so fascinating, which is precipitation. You say that life does not just receive rain, it summons it. All the water, biological detritus, and microscopic beings discharged by the forest form a massive floating river, an aerial echo of the one snaking through the understory. Can you tell us about this remarkable rainmaking and the role of microbes and life in summoning rain?
Absolutely. Yeah. It was learning how the Amazon rainforest generates its own rain was really the seed for the whole book. It was something that I learned many, many years ago, and it really inspired me to research similar examples. So the Amazon doesn't just passively receive the rain on which it depends, it actually generates about half of the rain that falls on its canopy each year. And the way this happens is so fascinating because it's about much more than trees and plants pulling water from the soil and then expelling huge volumes of water to the atmosphere. That's a very important part of it. But in parallel, the forest as a whole is spewing these invisible plumes of tiny biological particles, things like pollen grains and fungal spores and microbes and even fragments of leaves and insect shells. These particles are known as bioaerosols, and the wind sweeps them high into the atmosphere, and they accelerate the formation of clouds. Because clouds form when there's water vapor and when there's particles for that vapor to condense onto. And in some places, those particles are just inert bits of dust and soot. But anywhere where there's dense vegetation or dense life like the Amazon, it's actually biological particles that are much more important for the formation of clouds. And then some of this biological confetti in the air is even seeding ice crystals within clouds. And that makes the clouds larger, heavier, and more likely to burst. And so most of the rain that falls on land, even in hot tropical regions, actually begins as an ice crystal inside a cloud and then melts on the way down. So these biological particles are hugely important components of the water system around the world, but they've only recently been fully discovered and appreciated and studied. And so learning about that completely changed the way I think about the relationship between life and Earth, because I started to see life as having a much more active role, not just passively receiving or experiencing the weather, but creating and conjuring the weather around the world. And so to better understand this phenomenon, I traveled to the heart of the Amazon rainforest to a research station called the Amazon Tall Tower Observatory. And there's a series of research towers there that scientists from around the world visit to study the atmosphere above the Amazon, to sample gases and particles above the Amazon rainforest, and study the relationship between the soil and the sky and the water cycle and all the life in the Amazon. The tallest tower there is about 1,066 feet. It's the tallest structure in all of South America. And I climbed this tower with some scientists. It's very intimidating when you get there and you're at the bottom of the tower staring up. I'd seen pictures and I knew it was going to be very daunting and extremely tall, but like actually being there, I started to question whether I'd made a mistake, whether I could actually do this. And they're very concerned about people being able to physically complete the climb and also being able to psychologically complete it so that you don't get stuck halfway up because you're paralyzed by fear. So they ask you over and over again if you're sure that you can do it, if you're sure you're not afraid of heights. By the 10th or 12th time they asked me, I wasn't as confident as I had been in the beginning. But you get to be harnessed to a rail. There are still really big gaps. You could fall through, slip through. There's not any sort of real safety barrier. It's not like a tourist attraction. It's a bare bones structure that's just, the minimum it needs to be to allow you to climb up, into the atmosphere. But I went with scientists who are very experienced, so I gained some courage from them. And then when you're at the very top, you can actually see the Amazon as this immense living network that is stretching to the horizon in a way I'd never experienced it before, because on the ground, you're just overwhelmed by the density of life and you're chasing this butterfly or examining this patch of moss or lichen. But at that top of the tower, you can see the systemic perspective of the forest and see how it is this living network stretching across an entire continent. So that was a really amazing experience for me and kind of brought together so much of what I'd been learning. Yeah, that whole trip was kind of the inverse of the going underground, the subterranean expedition that we've been talking about earlier.
Thank you so much, Ferris. And I'm glad that I was able to read about it. I don't think I'd ever be able to do it. So hats off. In fact, I also like the part when you talk about actually coming back down.
Yeah, on the way down, it reminded me of a really long hike and your legs are really tired and jelly-like at that point. It's actually more challenging on the way back than it was on the way up physically. And you're trying to race the rain because it was going to start thunderstorming and you have to get off the tower in a thunderstorm condition. So we were hoping to get back down pretty quickly.
Thank you. So there is so much poetry to the lovely prose in your book. And one section that really took my breath away was when you wrote, "Earth is a stone that eats starlight and radiates song, whirling through the inscrutable emptiness of space, pulsing, breathing, evolving, and just as capable of dying as we are." You speak so eloquently in your book of the planetary emergency we are living through, one of our own making. And so much of your book speaks to the raging against the dying of the light through different kinds of interventions, processes, from dealing with our plastic invasion, the magic of marine vegetation, to carbon capture, and preserving the nutrients in our soil. In the start of the book, you note that Earth is like music, an emergent phenomenon. It cannot be reduced to notes on paper, the shape of an instrument, or the dexterous movements of a musician's hands, but instead arises from the interaction of all its constituent parts. When the right sequence of notes is played, even when it is combined with other sequences in just the right way, we experience music. How can we maybe extend that music metaphor to how we can cope with what is coming, and how can that extend to our own interventions so that we do not create a cacophony of solutions or make problems worse. And here also, I'd like you to share with us any parting thoughts that you may have, things that we haven't already covered in our conversation. But I have to say that I just love the music metaphor because it also brings into mind things like riffing and improvisation. All these things are so important.
Yeah, it was really challenging. It's so challenging to find the perfect metaphor for our living planet because it is the largest living system we know of, so it contains all other systems. And so it's like, which of those smaller systems do you choose to represent the largest system? And what I liked about music is that there's a certain kind of mystery to it, the way that there is with life. We don't fully understand what music is, but at the same time, we know it's a real physical phenomenon, just like life, but something we're still trying to fully define and explain. And both music and life have this emergent property to them, this sort of emergent nature to them, where they both arise from incredibly complex interactions of smaller components. And no single one of those components can fully explain the larger emergent phenomenon or produce it. It's only the interactions and relationships that can make this thing arise. And I found it particularly helpful in terms of thinking about rhythms and disruptions. Rhythms and cycles and feedback loops are so important to how our planet works, to Earth system science, to planetary ecology. And I wanted to really convey that sense in the book. And I think music helps us understand that because there are these long evolved rhythms. There are these co-evolved rhythms between the planet and life that are really important for maintaining the planet in a sort of habitable state and keeping it in a state that allows it to have a great diversity of life. And, familiar with many of the planet's rhythms, like that is what the day-night cycle is. That is a planetary rhythm. That's what a year is, how long it takes the planet to circle the sun. The tides, like breathing, the seasons, like there are all these incredible rhythms baked into the Earth system, and they guide and shape our lives. And so when those rhythms are disrupted, that is when we enter periods of crisis and we have to adapt very quickly. And, Earth has gone through intense, major catastrophic disruptions many, many, many times throughout its history. It's been around for 4.54 billion years. And we are now the latest cause of one of these crises. We have made this massive perturbation to the carbon cycle, and it is rapidly warming the planet and intensifying extreme weather and having all the other consequences that we're already living through right now. And so, in many ways, it's clarifying to think of the Anthropocene through that lens, that we have severely disrupted the planet's innate rhythms. We have thrown this giant living entity into severe imbalance. Our task is to restore those rhythms as best as we can. And honestly, one of the best ways we can do that is by backing off. We have to recognize that the Earth system has already evolved many incredible systems for sequestering carbon, for regulating climate. And these systems are what we call ecosystems. They're forests and grasslands and undersea meadows. So by simply not destroying those systems, we can do a lot to sort of help Earth stabilize itself. Unfortunately, that's not going to be nearly sufficient or fast enough to deal with what we have created because of the scale and speed of it. So we have to do a lot more than that now. What we have to do is to cancel out these immense sources of greenhouse gas emissions, so namely fossil fuels and industrial agriculture. These are the two largest sources of greenhouse gas emissions. They are the root cause of the severe disruption that we've introduced. So we have to replace and those, reform our energy infrastructure and our agricultural systems, and then at the same time get a lot more serious about conserving and restoring and protecting the planet's stabilizing ecosystem, the ecosystems that are already in place that sequester huge amounts of carbon on their own. And I think it's also helpful in thinking about, we have to accept that we've already changed the planet so much that it's never going to be exactly what it was before. But we can still preserve what we could call a variation on a theme. We can preserve a version of Earth that is familiar enough to us that we can continue a version of our way of life, even though it won't be exactly the same. I take sort of some inspiration from that it is still possible to preserve this variation of Earth that allows humanity to go forward and perhaps even eventually to create a better world, a more equitable world, a world that is powered by renewable and clean energy. And so, yeah, that's how I've come to think about it, really, is that we have severely disrupted the planet's rhythms. We have ushered in this period of extreme cacophony, of chaos. And we are seeing that happening faster and faster year by year. The storms, the wildfires, the deadly extreme weather events that are just in the news all the time now. But we still have enough time and opportunity to reverse that to some extent, to restabilize the planet's temperature and climate. But every moment that we delay, we make it so much worse. And so it really is about speed and expediency and scale. There's no time left to keep delaying. The wealthiest industrial nations that are most responsible for this disturbance have to lead the effort to correct what we've done. It has to happen as quickly as possible, because if it doesn't, it's just going to get worse by the moment.
I'm very curious because your book has just come out. I don't know that you're doing book tours and you're obviously talking about the book a lot with different people and also getting feedback. Now that you've written the book, because you cover so many wonderful topics in it, is there something that has surprised you at the end of it? Or is there something that you think you might want to do more research on in the future?
Yeah, I wish I could have had an entire additional chapter about coral reefs. I think coral reefs are so fascinating and important. I think they're actually really wonderful microcosms of the planet as a whole. Because a coral reef, I think a lot of people don't really understand what a coral reef actually is. First of all, they look like either rocks or plants to a lot of people. They have this plant-like botanical nature to them, but they're like rocky and mineral things. So I think a lot of people, they don't understand that they're actually these incredible symbiotic communal creatures. They're animal polyps that are related to jellyfish that are constructing these elaborate mineral structures and have formed a symbiosis with photosynthetic microbes and plankton, and they're all living together. And so they're basically a massive living rock, and very much like our planet is. And they're creating the substrate that new generations of reef need. So the very rocky structures they're making become the platforms that new generations of reef build on. So they really do resemble, immense living planet in a lot of ways. And I would love to learn and write a lot more about them and how important they've been throughout geologic time. There are many different types of reefs that have existed throughout geologic time, and they've suffered a lot of calamities, but they've always found a way to re-flourish, to re-emerge, to re-evolve. So I think they're very inspiring, chimeric, colonial, symbiotic creatures that we can learn a lot from. I'd like to write more about them.
Ferris, that sounds absolutely fascinating. And I love the idea of a reef as an imaginary. I want to really thank you for joining us. Reading your book was absolutely wonderful. Ferris, thank you so much. All the best.
Thank you so much.
Thanks to Ferris Jabr for sharing his thoughts with us. The Subverse is the podcast of Dark and Light, a digital space that chronicles the times we live in and reimagines futures with a focus on science, nature, social justice, and culture. You can follow us on Instagram at Dark and Light Zine. If you like the show, please tell a friend and subscribe on your favorite podcast platform. The Subverse is produced for us by Waka Media. So long, and thanks for listening.